Now let's learn the concepts of information transmission, information channels, and mutual information. First of all, let's have the notations. We have signal S, noise N, output O, such that O is equal to S plus N. The signal, for instance, may be input to a photoreceptor, and the output, for example, may be the response at a bipolar cell in the retina. The noise is added by the medium from the photoreceptor to the bipolar cell, and this medium is the channel from signal S to the output O. The signal S has this probability distribution, and we often omit the subscript to simplify the notation when the meaning is clear by the context. And similarly, the noise has this probability distribution. And these two probability distributions combine to determine the probability distribution of the output O using this mathematical formula. A given value O can be caused by all possible combination of signal S and noise N that sum up to its value O. So in particular, the conditional probability of O given S is equal to the probability that noise N is equal to the difference between O and S. The result of this summation is called the marginal probability. And so these two are also marginal probabilities, and these are just terms we use to call such probabilities. From observations O, we can infer S by this conditional probability distribution, the probability of S given O. Before we observed O, we knew nothing about S, so our ignorance about S is measured by this entropy HS, which is determined by the original or marginal probability distribution of PS. For example, if S is an integer within the range between 5 and 255, then HS could be up to 8 bits, and it is 8 bits if all these integer numbers are equally likely. Once we observed O, let's say we found that O is equal to 5, then the ignorance about S is now the conditional entropy defined by this notation. It uses the conditional probability of PS given O to calculate the entropy. It's using the same formula, except the marginal probability is now replaced by the conditional probability. Yeah. So for example, if noise is no more than plus minus 1, and if we observe O is equal to 5, and then S can only possibly be 4 or 5 or 6. And then the conditional entropy may be 1.59 bits if all these S values 4, 5, and 6 are equally likely. And you can see that 3 numbers give you entropy more than 1 bit. If there's only 2 possibilities, it will be just 1 bit. Yeah. If it's 4 possibilities, it will be 2 bits because log 4 base 2 is 2. Yeah. Anyway, let's continue. And so therefore, the information gained about S by observing O is the reduction of our ignorance from the original entropy to the conditional entropy. So in our example, the entropy went down from 8 bits to 1.59 bits. And so the information gained is then 6.4 bits. So the mutual information is defined by this information gained. So it is the difference between the original entropy HS before knowing O and the reduced entropy, the conditional entropy. Here the conditional entropy is the entropy is averaged over all possible values of O, not just when O equal to 5, but for all possible O values that we might observe. So normally the conditional entropy is this averaged term. And so again, the mutual information is the difference between this original entropy and the conditional entropy. And here is when we write out each entropy in detail using the original formula. And here is when we write the second term in another form, noting that the joint probability of O and S is equal to the marginal probability times the conditional probability. Let's now expand further, noting that the marginal probability PS is equal to the joint probability POS summed over all O. Now we can combine the two terms together since they are both weighted by the same joint probability POS. Now we can write it in another form. In this form, the S and O are non-symmetric to each other, so mutual information is indeed mutual between S and O. So we can switch the rows between S and O without any problem. So mutual information IOS is the same as ISO. Again, mutual means mutual. We can expand this term further, writing out each of the three factors inside the log in detail as a sum of three log terms. We can see that from the formula of entropy that this becomes the difference between the sum of individual entropies HS and HO and the joint entropy HOS. So, in summary, the mutual information is an important concept. It measures the amount of information in one variable about the other variable. The order between the two variables, which comes first or second, does not matter. The mutual information is always equal to the difference between the entropies of one variable without and with conditional on knowing the other variable. It is also equal to the sum of the entropies for individual variables minus the joint entropy. So, for example, if HO is 8 bits, HS is 8 bits, but the joint entropy is 10 bits, then the mutual information is 6 bits. And this 6 bits is the information shared between S and O.